Today we're going to learn part 2 of chapter 6, capacitance and inductance. The course objective is to analyze circuits with capacitance and inductance. The module objectives are as follows: calculate voltage and currents for capacitors and inductors in electric network with DC sources, combine capacitors and inductors in series and in parallel, analyze and design operational amplifier network with capacitors and inductors. First, let's look at how we can simplify networks of capacitors and inductors. Let's look at the first case when we have several capacitors in parallel. So since these are in parallel, current goes into this node is equal to the current leaving the node. There are several currents leaving this node, I1, I2, I3, until In. So we have this relationship IT is equal to the summation of all these currents leaving this node. At the same time, since they are in parallel, we know the voltage applied on these capacitors, they are all the same. We can use the voltage to calculate the current of the left-hand side and the current on the right-hand side. The current for this left-hand side, we use this equivalent network to calculate that current. So we assume there is an equivalent network like this, and this is the overall capacitance, and this current should be the same as this current, and the voltage should be the same as that voltage. And this current can be calculated by using the fundamental equation that we reviewed just now, Cp times the rate change of voltage. And on the right-hand side, we can calculate the current by using C1 times dV over dt, and the voltage that is the same voltage, so we have C1 dV dt. And the current I2 is equal to C2 dV dt. I3 is equal to C3 dV dt. And dV dt got cancelled on both sides. And we have the relationship Cp is equal to C1 plus C2 plus C3 until Cn. So now we can see that if we have capacitors in parallel, the overall capacitance is the summation of the capacitance of all these capacitors. You can also see this result from the physical meaning. Physically, we know that one capacitor is made of two plates facing each other, and normally in between that's filled with a dielectric material. Think of if we have another capacitor in parallel. We just add another capacitor over here, and it's the same thing as we extend the surface area. Putting two capacitors in parallel is equivalent to the case that we extend the area of one capacitor so that we increase its capacitance from the calculation of capacitance on the numerator that has the dielectrical constant times the area divided by the distance, right? So that is the area. Because we increase the area, the capacitance will increase. Now let's look at the second case when we have a series of capacitors in series. And when we have them in series, we know the current going through them should be the same current. And at the same time, from KVL, we know the voltage drop between the two nodes of this network should be equal to the voltage drop by following this path from here to here. So we have the definition of the voltage between these two nodes is equal to the voltage drop following any path. So if we follow this path, the voltage Vt is equal to V1 plus V2 plus V3 plus Vn. You can also understand that by using KVL. If we write a KVL for this loop, we know that V1 plus V2 plus V3 plus Vn, the minus V is equal to 0. And you put a minus V to the right-hand side, you will be able to get the same conclusion. So these are the two fundamentals that we have. And from this voltage relationship, that will allow us to derive the equivalent capacitance of this network. From the basic definition, current I going through a capacitor that is equal to C times dV over dt. And if we calculate the voltage, that will be equal to 1 over C times the integration of our current I dt. From this voltage relationship, for the first voltage on the left-hand side, we can find that from the equivalent network, which is equal to 1 over Cp times the integration of current dt, and this current is the same as this current. And similarly, V1, that is equal to 1 over C1 times the integration of I t dt. Similarly, the voltage drop on this capacitor C2 that is equal to 1 over C2 times the integration of our current IT dt. So we put them all together, we find that 1 over Cp is equal to 1 over C1 plus 1 over C2 plus 1 over C3 until the end. So let's just step back a little bit by looking at the conclusion that we have about the capacitors in parallel and the capacitors in series by comparing it to the conclusion that we have for resistor networks. So we find that for capacitors, if we have a capacitors in parallel, that is very similar to the way that we calculate resistors in series. And the way that we calculate capacitance of capacitors in series follows the same way that we calculate resistors in parallel. Let's look at the conclusions for inductor networks. So over here we have several inductors put in series. We can follow the same way how we derive the capacitance for capacitor network. And in this case, when they are put in series, the current going through the network will be the same. So the current going through this L1 is equal to the current going through L2. That is the same current. And for inductors, we know the voltage drop on this inductor is equal to L times the rate change of current. And we know the voltage drop Vt is equal to V1 plus V2 plus V3. And then we can add them all together. And at the same time, we can calculate the voltage drop from its equivalent network, which is equal to Ls times di dt. So di dt on the both hand side will be cancelled. So we find Ls is equal to summation of Li. Let's look at the second case when we have inductors placed in parallel. And what happens? Similarly, this is the current going into the node is equal to summation of the current leaving the node, right? So that is the relationship that we're going to use to derive the result. For inductors, the basic equation is the voltage is equal to L di dt. If we calculate the current I will be equal to 1 over L times the integration of a voltage. We replace the left-hand side by 1 over Lp times the integration of voltage, and right-hand side will be 1 over L plus 1 over L2, 1 over L3 until 1 over Ln times the integration of voltage. The integration of voltage will be cancelled on both sides, so that will give us a conclusion. 1 over Lp that is equal to summation of 1 over Lis. Compare the conclusion that we have for inductors with what we had for resistors. We find that the way to calculate or the way to simplify the network of inductors is exactly the same as how we simplify resistor network. If they are in series, the overall resistance will be the summation of them. If they are in parallel, the inverse of the total capacitance will be equal to the summation of the inverse of the inductance of all these inductors. The next topic will be operational amplifiers with capacitors and inductors. So here we have two applications. One is called an integrator. We have a capacitor in the feedback branch, which connects from the output end, this output VO, to the input terminal. If we connect this to the inverting terminal, it means the final answer will have a negative sign. If we connect this from here to the non-inverting terminal, we won't have this negative sign. So the conclusion that we have for this topic will be more or less the same as what we did for chapter 4, where we first learned operational amplifier circuit. The way to draw the conclusion is exactly the same as what we did before. Do you still remember how we analyze this operational amplifier circuits? So the first step we will state that we are going to use the ideal op-amp model. So we write down the ideal op-amp model conclusions, which is the nodal voltage and the two terminals are the same. At the same time, the current goes into the two terminals are the same and is equal to 0. The second step is to write nodal equations at the two nodes. By looking at this inverting terminal, we can write a nodal equation. This is the voltage V1 minus V minus divided by R1, which is the current goes into this node. The current goes into this node from the top branch. That is something new that we haven't done before. we know this node have a node voltage of VO, this node have a node voltage of V minus. So the voltage drop between this node and that node is VO minus V minus. And we know the current going through a capacitor is calculated by using the equation I is equal to C2 times dV dt. And this V over here is the voltage difference, which is also the voltage applied on this capacitor C2, which is equal to VO minus V minus. So you put that, and the summation of the current into this node from these two branches is equal to the current leaving this node, which is I minus, is equal to 0. And on the other terminal, because this terminal is directly connected to the ground, we know V plus is equal to 0. So by putting all this together, step 3 is to solve the equations, then you will be able to find the conclusion. So we find that VO is equal to negative 1 over R1 times C2 times the integration of V1t dt. So the second application is a differentiator. By comparing the differentiator to the integrator, we find that we just switch the location of the inductor and a resistor. So if we put a resistor on the input end, that will become a differentiator. So that is something you need to remember. So if we put this over here, it will become differentiator. The way to derive this conclusion is exactly the same as what we did before, so I'm not going to repeat the process. So next is the design problem. So by looking at the design goal that we want to have, the output is equal to 5 times the integration of V1 minus some signal V2. The first term, the integration from 0 to t, V tau, d tau, and the second signal V2. From here, it's still a little bit hard to tell whether you should put them on the two terminals or on the same terminal. It depends on whether you flip the sign of the first signal or not. We just learned the first term, how to get the integration. We know that if we put the capacitor from the output and connect it to the input, so we'll get an integrator, right? And we also know that if we connect this to the inverting terminal, the output will be inverted. So in this setup, the output from here, which will be the integration of V1 with some coefficient with a negative sign. It's a negative something integration of V1. On the right hand side, if that has a negative sign, but the output toward the end, this will become a positive sign. It means that we're going to connect this output to the inverting terminal. At the same time, for the second signal, V2, it has a negative coefficient. It means that we're going to connect V2 to the inverting terminal. At the same time, we bring a resistor from the output to the input so that it will allow us to adjust the coefficients. So this is the general idea about how we come up with an initial design. So the initial design is not unique. For example, I can put the V1 to the non-inverting terminal so that I want to flip this, so that I will keep V1 with the positive sign. In that case, you have positive something minus V2. It becomes a subtraction. In that case, you will put the output of the first signal to the non-inverting terminal and put a V2 to the inverting terminal. You will also be able to design a circuit like that by using that template to achieve what's desired. Assume that we come with this initial design, then we can write the design equations. The design equations are from the basic circuit analysis to find the output relationship with the input. After we analyze the circuit, we find the output is equal to some coefficient times V2 with a negative sign minus some coefficient times this. And we simplify it a little bit, become some coefficient times the integration of V1 t dt minus some coefficient times V2 t. So this is called a design equation. After we get the design equation, we just need to compare the coefficient with what we wanted from the beginning. So the coefficient for the integration of V1t should be equal to 5, and the coefficient for V2, R4 over R3 should be equal to 2. So these are the equations that we can get by comparing the design equation with what we wanted, right? So we can see that there are only 2 constraints from this problem, but at the same time we have how many unknowns? 1, 2, 3, 4, 5. We have 5 unknowns to select from 2 equations. So it means that we have plenty of room to come with different designs. So over here we can select C2 that is equal to 2 mu phi, and select R4 is equal to 20 kilo ohm. If we select R4 is equal to 20 kilo ohm, R3 will be determined because R4 over R3 has to be equal to 2. So R3 will be equal to 10 kilo ohm. And at the same time, because we only selected 2 of them, we have 5 unknowns, 2 equations, so it means that we can select the values for 3 variables. So we can select R1 is equal to 100 kilo ohm. By selecting all these 3, we'll be able to solve the other 2. So this is how we select the resistors. And this problem doesn't have any other requirement, but in practical applications, normally there are other requirements. I'll give you an example of that. You might have a requirement on the current will be less than 1 milliamp. So how do we calculate the current? So the current will be calculated by looking at the connector of the resistor network. So if all the voltage are giving 10 volts, so we can calculate the current going through the resistors, and we find the current going through the resistors in this case will be less than 1 milliamp. From chapter 4, we learned a couple of different requirements. We did the requirement on current, and we also did the requirement on the power assumption.